Okay, students, in the last class, actually, due to some technical problems, again my video is deleted, so again I am doing on the same topic, that is the electrical and magnetic properties of the solids. Okay, so first I'll explain the electrical properties of the solids. Okay, so here in the electrical properties, the conductivity of the solid is in between 10 raised to minus 10 raised to minus 22, 10 to the power 7 ohm inverse meter inverse. Okay, so this is what? The conductivity range. There are 28 conductivity range at different amplitudes are there. Okay, 10 raised to minus 22, 10 raised to 7. So in this conductivity range, again the solids are classified into 3 types, that is conductors, okay, second semiconductors, okay, third insulators. Okay, conductors, semiconductors and insulator. So here what happens? Conductors ranging from 10 to the power 4 to 10 to the power 7 ohm inverse. Okay, conductivity ranges from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. Why it is ohm inverse means, you know, the unit for a resistance is ohm. Resistance means the opposition offered by the materials to the conductivity of the electricity. Okay, so that is what ohm. Here conductivity means it is opposite of a resistance, that's why it is ohm inverse. So semiconductor means where 10 to the power 4 or 10 to the power 6. Okay, so this is semiconductors range. Okay, so insulator means below 10 raised to minus 10 to 10 raised to minus 20. Okay, this is the conductivity range. So listen, conductivity means it is the property of the elements to allow the electric current to pass through it. Okay, so in solids, all metals are good conductors, I told you. So why means? Because it consists of positively charged metal ions, okay, which are surrounded by a sea of free electrons. Okay, here what happens? In a solid state also they consist of this type of molecules or a constituent particles. In a molten state again they have free ions. Okay, so in this case what happens? In the solid also they have free electrons. In the molten state also they have free electrons or free ions. Hence they are the good conductors of heat and electricity. So all metals, because we are discussing in the solid state chapter, means all the metals which are in the solid state have the conductivity range between 10 raised to 4 to 10 raised to 7. Okay, so because of the presence of the free electrons. And next one is insulator. Later I will discuss about semiconductors because it has some types also. So insulators means the conductivity range is very low. They are unable to conduct electricity. Okay, it is very less. Minus 10 to minus 20 means it is nearly negligible. Okay, so here what happens? They are not at all ready to conduct the electricity. Okay, so this type of conductors or this type of solid substances which opposes the electric current to pass through them, that is called as insulator, where range is 10 raised to minus 20 to 10 raised to minus 10. Okay, so as we comes to semiconductors. Okay, so semiconductor means it shows sometime an insulator property and sometime a conductor property. So the conductivity ranges between the conductors and the insulators. See, 10 raised to minus 10 is this, 10 raised to 4 is this. So after 10 raised to 4 it is conductor, below 10 raised to minus 10 this is insulator. The conductivity range of semiconductors is in between conductors and the insulators. Okay. When they become conductors, when they become insulator means that will based on the conduction and the valence. Okay, I'll write diagram here. Listen. Assume this is the conduction band and this is valence band. Okay, this is conduction band and this is valence band. Okay, and the energy between them is, this is the energy gap required for a conduction of electrons jumps from conduction band to valence band or valence band to conduction band like that. Okay, so listen. Conduction band is there, valence band is there. When they act as an insulator, when they act as a conductor means. Okay, listen. So here is the conduction band. Here is the valence band. So the energy between this valence band and conduction band is very less. Okay, so listen, first I write here. For a conductors, they are merged. For conductors, there is no energy gap. The conduction band and the valence band, they are merged. Okay, for insulators, they are far away from each other. The energy gap is very high, so the electron can't easily jump from conduction band to a valence bond. Okay, so valence band. So here what happens? Here conduction is easy, so energy gap is nil. Here the conduction is very tough, that's why they are insulator. This is conductor, this is insulator. Okay, so but here in semiconductor what happens means, whether it behaves as a conductor or an insulator, that depends on the energy gap between this. Okay, if the conduction band and the valence band has small energy gap, that enough to jump the electron from this band to this band, then they behaves as a conductors. If the energy gap between two bands are very less, then they act as a conductors. If the energy gap is too far away from each other like this, then semiconductor behaves as a insulators. Okay, so this conductors and this one is a insulator, that is in what? Semiconductor. So sometimes they show conductor properties and sometimes they show insulator properties. But we can enhance the conducting property of the semiconductor by adding the semiconductor with or by doping semiconductor with any other elements. Okay, so what is meant by doping means, this is the important thing, doping. So listen, for example, for a semiconductor is I give silicon and germanium, they are the good semiconductor examples of a semiconductor, that is intrinsic semiconductors. Okay, so intrinsic means they are purely they are semiconductors. Sometimes based on the band they acts as an insulator as well as a conductor. Okay, they are pure semiconductor. So in semiconductors also two types are there, intrinsic and extrinsic. Intrinsic means these two, pure. Extrinsic means that is what I am telling, doping. So the impurities added to this type of intrinsic semiconductors to enhance their conducting property, so that is called as doping. Means the addition of impurity to the semiconductor, especially intrinsic semiconductors, called as doping. So doping means addition of impurity. Listen, silicon and germanium belongs to 14th group. Correct? Okay, so this group can be doped with 13th group elements as well as 15th group elements. Okay, if they are doping with 13th group elements, that is electron deficient group doping. So here electron rich group doping. Okay, so doping with electron deficient species, doping with the electron rich species. If this 14th group semiconductor, if it is doped with 13th group element, they form p-type semiconductors. Okay, so here 15th group, then they form n-type semiconductors. What is p-type? What is n-type? I'll discuss now. Okay, so this is all about the semiconductors and its conductivity. Now I'll explain which type of doping is there, why it is called as p-type and why it is called as n-type. Okay, so listen here for a p-type and an n-type semiconductor, silicon is there, belongs to 14th group, that is carbon family, means its valency is 4. Okay, so it has a 4 valency. Okay. Next, another silicon. This is a pure intrinsic semiconductor. Okay, so here what happens? If any one of these intrinsic semiconductor is doped with electron deficient species, that is 13 group elements, either boron, aluminium, whatever it may be. Okay, so I'll choose aluminium here. Okay, aluminium has how many valence electrons in the outermost shell? Means of course it is a 13 group. It has only 3 electrons. Okay, so here each silicon form a bond with further electrons of the other silicon. Here also with the aluminium. If another silicon is there, it also forms same thing. They form the bond with the other electrons. So silicon is a tetravalent, means it has the capacity to form a 4 bonds like carbon. So here what happens? The silicon, it may bonded with other atoms like here, but here with the aluminium, here one electron is less bonded with this silicon atom. So then what happens? This is what is less here means electron. Okay, so electron less means it creates a positive hole. It creates a positive hole. So then what happens? Here the electron from silicon shifts here. Okay, here it creates a hole. Okay, again this electron shifts here and here it creates a hole. Okay, the hole, the electron shifting to the positive hole and creating other hole at the previous position. So in that, by creating the hole and the positive hole in entire extrinsic semiconductor, so this shows conductivity. So here we are considering a positive hole here, so that's why it is p-type semiconductor, because one electron less means positive. Why it is positive means it creates an empty space for an electron. If electron wants to occupy their things, that must be a positive in charge. Hence this is called as a p-type semiconductor. When this p-type of semiconductor is formed, so listen, when the tetravalent species, that is 14th group intrinsic semiconductors, is doped with electron deficient species, that is 13th group elements. Okay, that's why this is called as p-type semiconductor. Okay, next one is n-type. Again, I write same silicon with the 4 electrons. Okay. So here what happens, students? One year, when the intrinsic semiconductor, that is 14th group elements, silicon or germanium, are doping with the impurity of pentavalent species. This is trivalent, this is pentavalent, 15th group elements, this additives. Okay, like nitrogen, phosphorus. So those species. So I have written phosphorus here. Okay, so phosphorus has 5 valency. Okay, here 1, 2, 3, 4. Okay, each silicon atom bonded the bond with the 4 atoms of the 4 electrons of the phosphorus. So being a pentavalent species, so 4 bonded atoms with electrons, it has another one extra free electron. So this free electron from the phosphor acts as a current carrier. So in this type of semiconductor, electron is more, means electron is negative in charge. That's why this is called as n-type semiconductor, because here electrons are the charge carriers. Here holes are the charge carriers. So this type of semiconductor is formed when the electron-rich pentavalent species is doped with the intrinsic semiconductor. So this is all about the n-type and p-type semiconductor. There may be a chance of us the difference between the n-type and p-type semiconductor. So you can write here n-type means, so in that this type of semiconductors will occur when the pentavalent, intrinsic semiconductor is doped with electron deficient species. So n-type means when the intrinsic semiconductors are doped with pentavalent species. Okay, here holes are the charge carriers, here electrons are the charge carriers. Okay, so this is all about the semiconductor. Next, what is the uses of semiconductor? Means semiconductors are used to prepare diodes. Okay, so diodes and NP, PNP transistors. Okay, so for these reasons, if instead of this, if gadolinium is used for this 13th group element, instead of boron, aluminium, gadolinium is used. Instead of 15th group, phosphorus is used. So then they enhance the property of the semiconductors as a conductors. Okay, so these are all the about the electrical conductivity property of the solids. Okay, so this is electrical property. And the last one is the magnetic property. I already explained, but due to some technical problems, you may not get clearly about the magnetic property of the solids. So again, I'll explain. Okay. Next one is magnetic properties. Okay, listen students. In the magnetic properties of the solids, the first thing is we have to know the magnetic moment. So how the magnetic property in solids happens means, listen. Metal consists of the atoms, right? And an electron. So due to the electron only the magnetic property will calculate. Okay? So the magnetic property of solids is shown by the electrons. Listen. Electron is rotated around the atom, that is orbital moment. At the same time, it rotates along its own axis. That is orbital along its own axis. So these two are movement of the electron results in the magnetic property. Okay, so this will be calculated by a magnetic moment with the formula square root of n into n plus 1 over magneton. Okay, so this is the formula to calculate the magnetic moment. So this is enough, not much. So based on this magnetic moment, the solids are classified into 5 different types. So in that I already clearly explained. One is paramagnetic. Okay, paramagnetic. Second, diamagnetic. Third, ferromagnetic. Fourth, antiferromagnetic. Fifth, ferrimagnetic. Okay, so in the paramagnetic, we are considering unpaired electrons. Okay, unpaired electrons are present in a solid, then that is said to be a paramagnetic, and it is weakly attracted by magnetic field. The examples are Fe plus 2, Cu plus 1, Fe plus 3, etc., which one has unpaired electrons. Okay, so for a paramagnetic, if a solid consists of unpaired electrons, then it is said to be a paramagnetic substance. And when the magnetic field is subjected to it and they are deeply attracted by the magnetic field, example for them is Fe plus 2, Cu plus 2, Fe plus 3, etc. Okay, and next, diamagnetic means they consist of paired electrons. Okay, if paired electrons are there, if they are subjected to the magnetic field, so they are weakly repelled by magnetic field. Repelled by magnetic field. Example: H2O, NaCl, etc. Okay, so listen. This is weakly attracted by magnetic field. This is weakly repelled by magnetic field. So when we subject the or apply the magnetic moment or a magnetic field in this direction, means this is also move in this direction, or the substances also shows the magnetic moment in the same direction in which the magnetic field is applied. So here they are weakly repelled, means if the direction of the magnetic field in the above direction, their magnetic moment is in the below direction. Okay, that's why both get cancelled and the magnetic moment becomes 0 for them. Okay, so next one is ferromagnetic substances. I told you for these two we are considering only electrons. For these ferromagnetic substances, we are considering what? Domains. Okay, so initially I told you domains are randomly arranged in a different directions, so the magnetic moment may cancel each other and become 0. So once we apply magnetic field to this type of substances, they are randomly arranged, randomly oriented. Domains are oriented in a proper parallel direction. Okay, once the magnetic field applied, they are oriented in a proper direction and they become permanent magnet. So once they become permanent magnet, means either the presence of the magnetic field or the absence of the magnetic field never affect the ferromagnetic substances. So they are strongly attracted by magnetic field, right? Strongly attracted by magnetic field. Example: iron, cobalt, nickel, etc. Okay. And next one is anti-ferro. So diagram is this. Okay. So here also we are considering a group of electrons called as bromines. But the one thing is here in anti-ferromagnetic substances, the equal number of parallel and anti-parallel oriented domains are present. Okay. So equal number present means the magnetic moment produced by this will cancel by this and this will cancel by this. So the net magnetic moment may equal to 0 or less. Okay. So because this is quite similar to the diamagnetic substances. So of course they are weakly repelled by magnetic field. Example is MnO. Okay, and the last one is ferrimagnetic substances. So here so in ferrimagnetic substances, what happens here? Also, we are considering again domains, but here unequal number of parallel and anti-parallel oriented domains will present. So listen, here three parallel oriented domains are there, one anti-parallel oriented domain are there. So here the magnetic moment may of these two may get cancelled, but they show some of the magnetic moment due to this type of domains. Okay, this may be a parallel or maybe an anti-parallel, but I am telling they have unequal number of parallel and anti-parallel domains. Okay, so here they show some of the parallel or anti-parallel direction and in the same direction or opposite direction means they are quietly similar to this paramagnetic substances. So they are weakly attracted by magnetic field. Example: Fe2O3, Fe2O4, etc. So listen, paramagnetic and ferrimagnetic are attracted by magnetic field. Giant antiferro is repelled by magnetic field, and ferromagnetism is strongly attracted by the magnetic field. And the last thing is these ferrimagnetic substances upon heating changes to paramagnetic substances. This is the one important thing, which magnetism changes upon heating, or to which magnetism ferrimagnetism changes upon heating. That is ferrimagnetic to paramagnetic. Okay, so this is all about the magnetic properties of the solids. Okay, so this completes the chapter solid state. Okay, now I'll write whatever the important and expected questions in this chapter they ask in the examination. So note down the questions, keep on practicing them, you may get the idea. Okay, so first question is difference between crystalline and amorphous solids. Difference between crystalline and amorphous solids. Second, Difference between Frankel and Schottky defect. Difference between Frankel and Schottky defect. So again, difference between N type and P type semiconductors. Okay, next. Calculation of number of atoms per unit cell in FCC, PCC, SCC and ECC. Among these four, anyone is compulsory for the annual examination. Among these three, anyone is compulsory. Okay. Next, fifth, calculation of derivation of packing efficiency in FCC, PCC and SCC. This is important for 3 marks and all are important for 2 marks. Okay, next problem based on formula D is equal to certain divided by AQ NA. Only these questions is compulsorily a must and should ask from this chapter. Okay, listen. I told you initially when starting this chapter, the one question is the question number 11 for 2 marks. Second question is question number 27 for 5 marks. In this 3 plus 2 is there. Okay. So this 3 marks question may be the packing efficiency as a formula. Problem or a packing efficiency. This 2 marks question from year and year is from either PCC or a difference. Means if they ask differences here, they may ask packing efficiency in the unit cell calculation. If they ask unit cell calculation here, they may ask problem here and the difference between the any type of substances or a semiconductor or a defect or a solid here. Okay, so here this is the pattern. So in chemistry, there is no one question is directly asking for 5 marks. Okay, it is always be 3 plus 2 or 4 plus 1 or 2 plus 1 plus 1 plus 1. We don't know in which type they are going to ask. So, but one thing I am telling, like physics, like chemistry, and like biology, there is no one question in chemistry is directly for 5 marks. It is always standard is for 3 plus 2. If not, it is 2 plus 1 plus 1 or 4 plus 1. Okay. So this is the solid state chapter. So this ends the first chapter. I will start with the next chapter in the next class. Thank you.